Hi, welcome back. Today we're going to move into the last section of the notes, which should take about the next week or so, which is vector spaces over the complex numbers. Okay, so I'm calling it complex vector spaces here. And remember that just a couple of days ago, we were talking about how call that linear algebra works over any field. You, of course, learn it over R to start with because you have geometry, you have nice pictures, you have good intuition. But all the theorems you learn from 308 work over any field, right? So we just took a look at an example where Z2 was very natural, right? When we were looking at error coding theory, error correcting codes, the Hamming code, it was very natural to think about Z2. There's also a nice way to picture vector spaces over Z2 as the corners of the unit hypercube. Um, so maybe I should say, like, first we start with R. This is what we start with generally. And then maybe the next most important field to do linear algebra over is the complex numbers. And it is true that you can do linear algebra over any field, because I've been saying that several times now. But one thing that you need to think hard about is notions of distance and of angles, because that's not linear algebra. Uh, that's really geometry, right? So linear algebra is okay, but here, what can we say about distance, angles? Maybe I'll lowercase. And remember, both of these are related to the dot product over R. So I'll ask about the dot product because these things are not linear algebra things. And that's some of what we need to talk about in order to develop some interesting tools over the complex numbers. Um, so what we're heading toward is we're heading towards these concepts as well as trying to understand the analogs of some of the things we learned about for real matrices, like symmetric matrices and things of that nature. Okay. Um, First, though, we should make sure we're all on the same page. Do a brief review of complex numbers, which we talked about a little bit earlier in the class, but now they're the main point of this section of the notes. So let's just recall that a complex number, usually use the letter z for a complex variable, is of the form a plus bi, where a and b are real numbers, and I squared equals -1. Okay. You call a here is the real part of z, and you call bi the imaginary part. Right, and so sometimes you'll say that the real part of z is a, which you'll notate like this, and you can say the imaginary part of z, is bi. Okay, so we'll need to talk about things like that sometimes. And the sum and product of complex numbers. So every complex number looks like this. You just add the real parts, and you add the corresponding imaginary parts. And then the product, you just, since complex numbers form a field, right? It means that addition distributes over multiplication and everything is commutative and associative. And so you can just multiply this out and then use the fact that I squared equals -1, right? So here you'll get, I guess we should just do it, AC plus ADI plus BCI plus BDI squared, right? But I squared is -1, so you get a real part of AC minus BD plus a real part, sorry, an imaginary part of AD plus BC times I. Okay, and let me just put this on this slide because this is all still recalling stuff. For any complex number, the complex conjugate is also a complex number, which we denote with a bar. And so since z here is a plus bi, z bar is a minus bi. So you just take the same real part, but you take negative the imaginary part. Okay, and this is going to be an extremely important operation on complex numbers. And also recall that if you have a real number, then it's equal to its complex conjugate. Right? So if x happens to be a real number, remember the reals sit inside the complex numbers, then it is equal to its own conjugate. This is, in fact, another way to characterize the real numbers. The real numbers are exactly the complex numbers which equal their own conjugate. Okay. Now the standard way to visualize C is as a two-dimensional vector space over R, which it actually is, by the way. I should say, maybe this is worth commenting, that as a vector space, C, maybe I should say as an R vector space, C is two-dimensional. Sorry, two-dimensional. Right? C is the span, the R span of 1 and I. And so you take all possible R linear combinations of 1 and I. So as a vector space over R, it actually looks just like R2. But it's not R2, it's C, because C also has a multiplication. You can multiply two complex numbers. It doesn't make any sense to multiply and get a complex number. It doesn't make any sense to multiply two vectors in R2. So as an R vector space, it's just R2, so it looks just like R2. What makes it C, though, is that you have an additional operation, a multiplication, and you also can get multiplicative inverses of non-zero complex numbers. Okay, so as an R vector space, C is just isomorphic to R2, but there's more structure here. So we also have multiplication, which distributes over addition, and multiplicative inverses. Right, I guess I never defined this symbol. This just means is isomorphic to. But what I mean by that is that they're the same vector space. But that means that we can visualize C as a plane. So the standard visualization of C is as a plane where the horizontal axis is the real axis and the vertical axis is the imaginary axis. And again, we said that every complex number is some real part plus some imaginary part, which you just graph in the way that you expect, right? So if you have the complex number z equals a plus bi, you graph that as here's a, here's b. That point is a plus bi, which you can think of, if you're thinking of it as R2, right? You can think of this as the vector AB. But since it's a complex number, you call it a plus bi, right? And so it's very standard to visualize the complex numbers as living in the plane like this. And what does conjugation do then? Well, conjugation just negates the imaginary part. So z bar has a coordinate of negative b here. This is z bar. And so you see that what conjugation does is it just flips across the real axis. You just treat the real axis as a mirror and flip across, which is another way to see that the real numbers are exactly the complex numbers that are equal to their own conjugate. That's exactly the mirror, right? The real numbers are the mirror here. Okay, so we'll see a little bit more about how to think about this visualization. But let me just point out some nice properties of complex conjugation. So if you take some properties. So if you take z plus z bar, right, that's a plus bi plus a minus bi. So you get 2a, which is 2 times the real part of z. So this is one nice way to pick out the real part of z. You add it to its conjugate. Of course, if you subtract them, z minus z bar, you get a plus bi minus a minus bi. So you get 2bi, which is 2 times the imaginary part of z. This is hopefully well known to you, even from calculus, that if you multiply a complex number by its conjugate, the nice thing is that you get a real number. So that's a nice way to produce real numbers from complex ones. And then conjugation satisfies some nice properties. So if you take the conjugate of the sum of two complex numbers, it's the same thing as taking the sum of the conjugates. And if you take the complex conjugate of the product of two numbers, it's the same thing as taking the product of the complex conjugates. Okay, so complex conjugation is an extremely important feature that the complex numbers have, and these are the most used important properties about it. Okay, but once you think of C like this, you realize that there should be a notion of length for complex numbers, because there's definitely a notion of length in this picture. And eventually we should have a notion of length for vectors even in C2 or C3 or C to the 4 or Cn, right? Now just for a complex number, so this is a notion of length. So if z is a complex number, then the length or the modulus of z is, so you use the absolute value bars, but you say the modulus, you don't say the absolute value of a complex number, you say the modulus. And what it is it's just z times z bar. It's just square root of z times z bar, rather, square root of a squared plus b squared, which is exactly the length. That's exactly the length of this vector thought of as a vector in R2, right? It's the square root of a squared plus b squared. It's just a nice way to get this is to multiply z by its conjugate and take the square root, of course. Okay, so we have a notion of length for complex numbers. Right, so this is the same thing as the Euclidean length of the vector a plus bi in the complex plane. Okay. Right. This should really be done earlier, but another fact is C is a field. I guess one thing that isn't obvious is every non-zero complex number has a multiplicative inverse. Okay, and this is just something that you kind of need to play with. But if z is equal to a plus bi, then right, of course, it's non-zero, so you can't have a and b both be 0. But so it's 1 over a plus bi, and you can multiply it by the conjugate on top and on bottom, right? That's just multiplying by 1. So that's all I did there. So another way to say this is it's z bar over z times z bar, which is z bar over the length of z squared in C. Okay, so taking the conjugate is somehow kind of quite close to taking the inverse. It's almost the inverse, except you need to divide through by the length squared. Okay. Now, another thing that you get from this picture is we're thinking of complex numbers as vectors in R2, which normally you describe as an x coordinate and a y coordinate. But you learned in calculus probably that you can also think of the plane in polar coordinates as having like a length coordinate and an angle coordinate. And it turns out that this is actually extremely useful for complex numbers. So we could think of, you almost, when you first learn about complex numbers, you think of them as an x coordinate and a y coordinate. You think of them as a plus bi, right? 1 plus 2i, that's a complex number. But we can recoordinatize this plane in polar coordinates, and this would give us another expression of every point on this plane. In other words, another expression for every complex number. Okay, so the polar form of a complex number. So if z is a complex number, and we let r be the modulus of z, so again, the picture is, here's z, and the length of this vector is the length of z, so I'm calling it r. The point is that you can think of this point here as a point in terms of the angle theta it makes with the real axis here. Times the radius, the length, right? So you can think of this as r cosine theta plus I, let's put the r on the outside, I sine theta. Right, because the coordinates of this point, this is also r, the coordinates of this point, if you were thinking of it as a vector, would be r cosine theta, r sine theta. But we just said that the way to translate back and forth is the vector a comma b is the complex number a plus bi. Right, so that point is r cosine theta plus I sine theta. And a short way to write this is r e to the I theta. Yeah, which hopefully you learned in calculus, right? And it turns out that there are some reasons why you might want to use the a plus bi form of a complex number that is helpful for some computations or some ways of viewing the complex numbers. And there are some applications where the polar form is actually much more natural. Okay. So I actually think, yeah, if you're proving things in the abstract, oftentimes the polar form is actually more natural because somehow the polar form captures more of the geometry of what's happening, I think. You'll see exactly why, because in terms of multiplication, the polar form captures the geometry much better. In terms of addition, I think probably the rectangular form, the standard form, is probably more natural, I would say. Okay, but again, this conversion to polar coordinates is just what you learned in calculus, right? So if there's a nice example, let's just do that exact example. If you take the complex number 3 minus 2i, where is that in the plane? It's 3 units here minus 2 units here. It's this complex number. This is 3 plus 2i. How do I express this in terms of r's and thetas? Well, what's the length of the complex number? The length of this number is just the square root of z bar. So it's the square root of 3 squared plus 2 squared. So it's the square root of 13. So that's the r. Okay, what about the theta part? The theta is going to be this angle. Right, so if you think of it, this triangle has side length 3 here, side length 2 here, and side length root 13 here. So there's several ways to calculate theta. Theta is going to be, I think the best way to do it here is actually arc sine of opposite over adjacent. So negative 2 over root 13, because that'll return an arc sine in the correct quadrant, right? Yeah. You could also do arc sine of 3 over root 13, but I think you would need to take the negative of that. Uh, yeah, so I think there's actually a little error in the notes. It would be negative cosine or arc cosine of 3 over root 13. Because if you took the arc cosine of 3 over root 13, it would return the positive angle, and you want the negative one. Okay, now, this looks a little bit gross, I think, right? 3 minus 2i seems a lot nicer than root 13 e to the I theta, where theta is equal to arc sine of negative 2 over root 13. But, again, this form captures a different part of the geometry of this complex number. It captures the length, which is a very important feature of it, and it captures the angle from the positive real axis. And here's one of the main points, which is if you take two complex numbers and you write them in their polar form, so z is r e to the I theta, and w is, say, rho e to the I psi, let's say, then the product behaves as you would expect. If you were to multiply these together, you would have r times rho e to the I theta times e to the I psi, but that would be r rho e to the I theta plus I psi, which is r rho e to the I theta plus psi. Okay, you could actually prove this. It uses you'd have to use the cosine and sine sums of angles formulas, right? What I'm saying is you write this one as r cosine theta plus r sine theta, and you write this one as rho cosine psi plus I rho sine psi, and you can actually multiply them out and use the angular formulas for cosine and sine, and you'll get that it will exactly equal this. But what does this mean? This means that when you multiply two complex numbers, the lengths multiply and you add the angles. So geometrically, multiplication you can think of as a really nice thing. It's really easy to visualize the product of two complex numbers if you think about them in their polar form. You take two complex numbers, those are both vectors sitting somewhere out in the complex plane. The product will have length, that's the product of the lengths, and you just add the two angles together, right? So, I mean, I guess we can kind of draw that here. Right, so maybe r e to the I theta is here, and maybe rho e to the I psi is here. So this is theta. Maybe I should have done this in a different color. This is psi. Well, their product will be you add their angles. So actually, let's call this one z. Let's call this one w. Their product will be you multiply the lengths and you add the angles, and I guess the sum of the angles looks like it's going to be somewhere like around here, right? So this angle here, I mean, let's just say this is zw, this is r rho times e to the I theta plus psi. So actually multiplication, I think, has a more natural interpretation in terms of the polar coordinates than it does in terms of the rectangular coordinates, right? The rectangular coordinates, the expression for the multiplication was this thingy, which doesn't really have any meaning, right? It's just some expression in terms of A, B, C, and D. It's really hard to understand what exactly that means. If you think in terms of polar coordinates, though, it has a very natural expression, right? Which, by the way, also means that you can take powers, right? So z to the n, that's just like you multiply z by itself n times. But at every stage, you multiply the lengths and you add the angles, so you get this. That's the basic properties of the complex numbers we need. But remember, what we want to do is we want to do linear algebra over C. So now we need to think about vector spaces over C. So the first one to define is, of course, Cn. So now vector spaces. So the complex vector space Cn is just the set of all n tuples of complex numbers. It's the usual thing. A vector is just a collection of elements from your field. In this case, we're allowing complex numbers. Okay, so when I want to write a complex vector, I'm going to do it with a very clear arrow. Okay, so in the notes, the thing to do is to make them bold, because you can actually see bold in typing, but it's very hard to handwrite bold. But what I want to say is you want to be careful that it's clear when you're taking a conjugate, and it's clear when you mean a vector. So you should try to make your arrows very clearly arrows and not potentially bars. Okay? Now, that's what the complex vector space Cn is, but of course you need to know the addition and the scalar multiplication. But those work always the same way when you're talking about actually over any field. The way that you add two vectors is you add them component-wise. The way that you scalar multiply is you multiply into every component, right? So if z is this vector and w is this vector, and there's a natural sum, you just add each coordinate. And of course, if you add two complex numbers, you get a complex number. So that's n complex numbers. So that's again in Cn. And if now I take a scalar, which will look like a plus bi in C, then when I scalar multiply this vector by this scalar, remember, we're working over C, so the scalars are complex numbers. You just multiply into each component. Right. And each of these were complex numbers, so when you multiply them by another complex number, you're going to get a complex number. So this is also in this, I mean, that's also an n tuple of complex numbers. Okay, so null spaces work the same. Row reduction actually works the same. You just need to allow complex scalars. Column spaces, matrix of a linear transformation, all these things work over C. So over C, you can do null spaces, column spaces, matrices, like rank nullity theorem, like row reduction. That's all good because linear algebra works over any field. But what will be different is dot products. Okay, so remember when you took the dot product of two vectors in Rn, v and w, you took v transpose w. And that gave you a nice notion of a dot product. It turns out that that doesn't generalize in the immediately obvious way to complex vector spaces. In other words, we're going to define an inner product on Cn, but it's not going to be the inner product of z and w is z transpose w. It's going to be slightly different. So I'm going to introduce a very important notion, the notion of the conjugate transpose. Okay, and as you take more and more classes, you'll probably hear the phrase conjugate transpose like thousands of times. It's just the natural thing you do when you have a complex vector space, a complex vector or complex matrix. So if z, which is z1 through zn, is a vector in C to the n, then the conjugate transpose of z is, so you take the transpose and then you take the conjugate of every entry. Okay, so this is why I want to be very careful about arrows versus lines. So here, let me be extra careful. I'm taking the vector z, I'm transposing it, and then I'm taking the conjugate of every entry. So it looks like z1 bar, z2 bar, zn bar. Okay, so of course you can still take the transpose of a vector. You can still take the transpose of a matrix, even a complex matrix. That's just exchanging the rows for the columns. But it turns out that the conjugate transpose will actually be what we need in order to do geometry. And so uh, we'll adopt some special notation for this. Okay, so this thing, I'm going to define this thing to be z star. Okay, so I'm using star to mean conjugate transpose. It means take the transpose and conjugate it. Okay. Now, the point is that this is the thing that we'll use to define inner products and norms. So let's start with norms. So given z and c, c to the n, then the norm of z is defined to be, so I'll use this notation. Double bars always means norm, right? Single bar means modulus. That's like the notion of length in your field. This norm is a notion for vectors. It's like absolute value versus norm of vector, modulus versus norm of vector. This thing for real numbers was defined to be the square root of the dot product, so v transpose v. But I'm going to define it to be the square root of the conjugate transpose of z times z. Okay. So a couple of things to note here. First of all, why do we take the conjugate transpose instead of the transpose? Actually, no, maybe first of all, notice that if z happened to be a real vector, which you can think of as also a complex vector, then z star is the same thing as z transpose, because when you conjugate a real number, you don't change it. So this definition actually does generalize the real definition. It's just you didn't see the conjugation before, because if you conjugate a real number, it doesn't do anything. Right? So that means that this agrees with our definition of norm for Rn. It looked a little different. There was no star, but that's because the star wouldn't do anything anyway. Now the question is, why do we need the star there? And this is best to do by example. So let's do it by example. So if z is 2 minus I and 3 plus 5i, z transpose is, of course, just 2 minus I times 3 plus 5i, like this. But the conjugate transpose, so z star, try to make my arrows clear, is the conjugate of this thing. And the point is that if you take z transpose z, so like the naive generalization of the dot product, what you'll get is you'll get 4 minus 4i minus 1 plus 9 plus 30i minus 25. Right? I think I've done this correctly. So you get 12 minus 25, so negative 13 plus 26i. And the problem here is that norms should capture lengths of vectors, but the length of a vector should be a real number. Because you want to be able to compare lengths, for example. You want to be able to say, oh, this vector is longer than this vector. But the only reason that you can compare lengths is because there's an order to the real numbers. You know exactly when one real number is bigger than another. The difference with C is there's no notion of like 3 being a bigger number than 2 plus I. You don't have a less than or equal to on the complex numbers. So it does not make for a good notion of length and we would like the norm to be a real number. If you take the conjugate transpose, though, what you'll get is, I guess I should do this down here, z star z is just, you multiply these two and add them together, you multiply these two and add them together, but when you multiply a complex number by its conjugate, you get a real number. So here you'll get 5 plus 34, which is 39. And then you take the square root for the norm, of course, right? So the norm of z is square root of 39. So the reason to introduce the conjugation part of this is so that this norm will always end up being a real number, thereby giving us a useful notion of length. Okay, and this thing that's happening inside of the square root sign, this conjugate transpose of one vector times another vector, that's the notion of like a dot product that we'll have in Cn, which you don't see over R because taking conjugates over R doesn't do anything. Okay, so that's what I'll define. So given Z and W in Cn, the Hermitian inner product, and it's the most common, most used inner product over complex vector spaces, is defined to be Z star W. Again, this actually does generalize the old dot product. If these vectors were real vectors, you would get the dot product because taking the conjugate transpose is the same thing as taking the transpose. Okay, but like if we're being extremely explicit and we're writing down the entries of these two vectors in terms of their complex numbers, then the this dot product here, this Hermitian inner product here, is just Z1 conjugate times W1 plus Z2 conjugate times W2 plus Zn conjugate times Wn. Okay, so this will be the notion of dot product, but it's actually Hermitian inner product that we'll use for complex vector spaces. Let me give a warning that this inner product does not behave exactly the same as the dot product because there's a conjugate involved. So warning, don't assume any properties. Okay, so in particular, like we know that the dot product is commutative. In general, Z star W does not equal W star Z. Right? Why? W star Z is W1 bar Z1 plus W2 bar Z2 plus Wn bar Zn. And of course, multiplication of complex numbers is commutative, so you can move the Z's to the left and the W bars to the right. But this quantity and this quantity are not the same. They're conjugates of one another. So you're very used to thinking of the dot product as commutative, which it is. But that's because when you take the conjugate of a real number, you get back the same number. Really, the dot product is only commutative up to conjugation, is really what this is saying. It's just you don't see it when you're working over the reals. So don't assume properties just because it's an analog of the dot product that you learned about. Right, again, these are all notions of lengths and angles, so you need to be very careful when working over the complex numbers because things are slightly different. You didn't see it in the real picture, but you can see it when you think of them as complex numbers. Okay, but once you have a notion of inner product, then you have a notion of angles and a notion of lengths. We actually introduced the lengths first, right? Once you have an inner product, the length of a thing, the length of a vector, is you take the inner product with itself and you take the square root. But once you have an inner product, you can also talk about what it means for two vectors to be orthogonal. What it should mean is that their inner product is 0. That was what was true for the dot product case, and that will be our definition, in fact. Right, so we say that two vectors, I guess I'm saying u and v now, are orthogonal if u star v equals 0. Which, by the way, is equivalent to v star u equaling 0. Because you would get the conjugate of 0, which is 0, because it's a real number. Okay, so the good thing is if you just want to know if two vectors are orthogonal, you can take the inner product in either order, because if one of them is 0, the other one will be 0. But again, you want to be careful. You don't want to just flip inner products willy-nilly, because they're not the same. You can't just commute them past one another. Okay, and we might as well, while we're here, so we'll say that two vectors are orthonormal, or a set of vectors will be orthonormal. That should just mean orthogonal and norm 1, which is exactly what it means. So if u star v equals 0, and the norm of u and the norm of v, those are both 1. So we'll be able to talk about orthogonal sets of vectors and orthonormal sets of vectors over C because we have this notion of an inner product. Okay. I think this is basically the intro, the background stuff for the more interesting, complex vector space theorems that we're going to prove next time. So I guess I'll stop here. Really, not so much new today. Hopefully you've seen complex numbers before. I recommend that you get comfortable working with them just in general, in lots of classes, math and otherwise. It's very useful. The only really new definition today was the conjugate transpose and this Hermitian inner product and the Hermitian norm, which is based on the Hermitian inner product. All right, so next time we'll talk about the complex spectral theorem, and then we're going to move toward some Fourier transform stuff as we end the course. See you next time.